Okay, so we've learned about all of the different kind of losses we can have in a system. So now we're going to apply this towards a somewhat practical example, which is we have a large tank of water. We're going to use it, let's say, to um, water some plants or something like that. Who knows? But we need a flow rate of 1 liter per second. So 1 times 10 to the negative third meters cubed per second. And the length of the pipe coming out of this reservoir is 1 meter, has a diameter of 1 centimeter, and a surface roughness of 0.00025 millimeters. All right, so um, first thing we need to do is we need to talk about what model we're going to use and what assumptions we're going to use. So the equation we're going to use is our modified conservation of energy equation, right? Equation 1 then is going to be P over rho G plus V squared over 2G plus Z out is equal to P over rho G plus V squared over 2G plus Z in plus H pump plus the sum of all of our head losses. Excellent. So you'll notice that we need a velocity in this equation, and we also need pressures and all that stuff. So first thing we got to do anytime we're using conservation laws is we have to draw our control volume. So the way I'm going to draw my control volume, it's already drawn here, but I'll redraw it in solid red, is I'm going to surround the inside of this. I'm going to cut across the exit, right across the jet. I'm going to come up, come right along the surface, and then come down like that. So that way the pressure on my in is atmospheric pressure. So we're going to assume, by the way, a steady state, because remember we have to assume steady state in order to use this form of the conservation of energy equation. B, uniform properties. So that way we don't have to do the integral across any of our control volume surfaces. We're going to assume further A in is much larger than A out, and we're going to use gauge pressures. So if we're using gauge pressure, we can cancel out both of our P's because our pressure in is at the surface of the water and our pressure on the out is cutting across a free jet, and the free jet has the same pressure as the air around it. Our velocity in is going to be much less than our velocity out, so I'm going to cancel that out due to C. We know our V out because we know our flow rate, we know our diameter, so we can calculate that. Our Z out is going to be 0 because of how we've chosen our coordinate system such that our Z out is 0. And our Z in is what we're solving for because we want to know what height is required to get our flow rate Q. There's no pump in our system and we just have to worry about our flow rates. Excellent. So the first thing we're going to do is we're going to include only major head losses. Okay? So only major head losses. In that case, HL is going to be equal to F L over D V squared over 2G. So in this case, we still need our velocity. We know our length, we know our diameter, G, and that means we have to find our F as well. So let's calculate our velocity real quick. Q is equal to, this equation 2, Q is equal to V times A. Our flow rate is equal to our velocity times our area. So our velocity is going to be equal to our flow rate divided by our area, and that is going to be equal to 12.7 meters per second. Excellent. So now we have our V out, and we have our V for our head loss. And note that this V is the velocity for our head loss, is the velocity within our pipe. So sometimes we'll have multiple pipes, we'll have different V's for our different head losses. Great, now we just have to figure out our friction factor. So we're going to go through and we're going to do our steps for our friction factor. And so at this point, you should either have the equation ready excuse me, the implicit equation or the explicit equation ready, or a Moody chart ready, however you decide you want to solve this. So the first thing we do is we find our Reynolds number. RE is equal to rho VD over mu, which in this case, I'm going to hope you pause this video and then try to calculate it before I do. Okay, and it is 1.2 times 10 to the fifth. 10 to the fifth. No units on that, right? Because it's a dimensionless parameter. And so 1.2 times 10 to the fifth is turbulent flow. Great. That's wonderful. Remember, we had two options, basically. We have laminar flow, where the Reynolds number is less than 2100, where our friction factor would just be equal to 64 over the Reynolds number. Or Reynolds number is greater than 4000, in which case we have our implicit equation, which is listed right here, our implicit equation, or our explicit equation, which is slightly less accurate. Cool. So we have that. Now we find our E over D is equal to 0.00025 millimeters divided by 10 millimeters. And the mistake I see most often on the exam is people forget to make the top and bottom have the same units. They'll just plug in 1 centimeter on the bottom and they'll be off by a factor of 10. But this ends up being equal to 2.5 times 10 to the fourth. So it's a fairly smooth pipe. Fairly smooth pipe. Again, that's unitless, right? Because it's a pi group. And then we find our F. And however you plan to do it, go ahead and try that now. Pause the video, go ahead and plug it in, and I will tell you that I got F is equal to 0.018. Awesome. So now what's wonderful is we have an equation where we know everything. We now know F, L, V squared over 2G. We know diameter. We know the velocities. The only thing we don't know is Zn, and so we're going to solve for that, and we find out that H is equal to Zn is equal to 23.7 meters, which is very high. That's what, on the order of 60, 70, probably actually closer to 80 feet. What's really interesting is if we were to use Bernoulli's to solve this problem. Remember, Bernoulli's assumes an inviscid fluid. So that would be without losses. We would get that Zn is equal to 8.23 meters. So our major losses consume a tremendous amount of energy, right? This 8.23 is the kinetic, essentially like kinetic energy. It's not, remember, it's not the units of energy because we're dividing by rho and g, but it's you can think of it as proportional to the kinetic energy of the system. So without losses, all the potential energy goes into kinetic energy. But with losses, we have nearly 200% more energy necessary because 200% of the kinetic energy is lost to viscous losses, which is a lot of energy. So what happens if we add minor losses? Well, in this case, if you look at this diagram closely, I drew the pipe entering into our tank. So it's a reentrant entrance, and reentrant entrances are terrible. They're terrible for the reason that fluid has to come around and do a 180-degree bend in order to get in here. And remember, fluids don't do a 180-degree bend. So they won't even do a 90. Heck, sometimes they won't even do like a 30-degree bend. So they come around like this, they separate, and they reattach sometime later, but you get large eddies in this region here, which do several things. One, they make the diameter of this narrower, the apparent diameter narrower. So remember, we actually solved for, if you cut the pipe off here, we actually solved for the diameter that this would be, and it's half the diameter of the actual pipe. So you get a large decrease in apparent diameter at the entrance, but you also get a lot of turbulent effects that then propagate through the flow. And like we said, the way the entrances to a pipe can really affect the nature of the flow. So you lose a lot of energy from a reentrant entrance. And the minor loss coefficient for this KL is equal to 0.78. So in that case, we come up here and our head loss then is now equal to HL is now equal to FL over D V squared over 2G plus KL reentrant, which I've just put an R there, times V squared over 2G, where KL is 0.78. And in this case, you have to be careful what velocity you use. If you look it up on a chart, the chart will tell you what to use. You just have to trust the chart. And in this case, KL is going to be equal to 0. The velocity for this KL is the average velocity in the pipe after the entrance. So it would be 0, same velocity as for our major head losses. So we can just plug in the same velocity there as we were using before. And when we do that, in this case, we know everything, right? We know K, we know V squared, we know 2G. We have to just now resolve for H. And what we get is that Zn is now equal to 30.3 meters, which is a lot higher, right? So we went from 23.7 meters up to 30.3. So our major head losses was roughly equal to 15 meters worth of loss, right, of energy. And our reentrant entrance then is roughly equal. Reentrant entrance is roughly equal to 7 meters of energy. So it's almost half of what our major losses were, just by doing the easy thing, which is to drill a hole in a tank, slide a pipe in, and then caulk around the outside and be done, right? Or weld if it's metal. Just by doing the easy thing, we increased our losses by 50%. We increased our losses by 50%. So what happens though if we spend more money and get a rounded entrance? So in this case, we'd cut a bigger hole. We have to be more careful when we weld it. In this case, you'd have to definitely weld it. When you attach it, you have to be much more careful. But if we use a rounded entrance here, we have K is equal to 0.04, which is orders of magnitude, like 20 times less than 0.73. And remember, when we do this, the fluid's very happy because it just goes around the bend and enters the pipe. Because it can take gentle bends very easily. It can't take 90-degree bends, but it can take gentle bends very easily. So we don't get any of that initial flow separation. We don't get the vortices. We don't get the area decrease. Everything is much more well behaved. And so when we solve for, when we plug in our new K value into our equation, because remember our head loss, we're going to rewrite it just because it's a good thing to repeat it over and over again. FL over D V squared over 2G, that's our major head loss. That doesn't change when we change our entrance. But what does change is our KL V squared over 2G. So before we had 0.74 in here, now we're going to plug in 0.004. And when we solve for our new Z using that, we find out that our Z is equal to 24.2 meters. So we went from about 7 meters to like 0.5 or 0.4 meters of energy loss. Huge change, right? Just an absolutely huge change. Yeah. Cool. So hopefully this shows you how just a simple change to the type of entrance you have can really change the amount of losses you have in a system. And this is especially true for valves, for example. Like most places have a tremendous number of valves in order to control flow. They have one valve, they might have a backup safety valve somewhere else. You have just all kinds of valves, and each of those valves, depending on what you use, is going to add a minor loss coefficient. And different valves have different minor loss coefficients, and you can end up with quite large minor loss coefficients if you use the wrong kind of valve. For example, diaphragm valves are very quick valves, so they switch on and off very quickly. But the way that they're constructed is you have a flow that comes up like this to a chamber, and then it comes down. And what seals it is a diaphragm that gets pushed down across these entrances. And then when it's open, it comes up like this. So when it's open, let me erase both of those. But when the valve is open for a diaphragm valve, right, it looks something like this. Your flow is coming up and around this narrow constriction and then back down. Obviously, you're going to have flow separation. You're going to have all kinds of turbulence added, and you have a narrowing, a natural narrowing, in addition to any kind of flow separation that's occurring. And so the losses on diaphragm valves are much higher than, say, for a ball valve, which is can be quite low when it's completely open. Butterfly valves are somewhere in between, but are cheaper than a ball valve. So yeah, there's lots to consider when you're building a fluid system. Finally, let's say you've realized it's kind of ridiculous trying to build a high enough tank in order to get the flow rate you need. So you've decided to add a 200-watt pump that is 80% efficient to your system. In that case, now we get to use. Let's write out our equation again, since it's been a while since we've used it. We have P naught over rho g plus v squared over 2g plus z out is equal to P over rho g plus v squared over 2g. This is not P naught, sorry. Over g plus z in plus an H pump plus H losses, right? Adding a pump is not going to change our losses, but what it will do is it'll add something in for our H pump term here. And so remember before we had our lowercase w dot pump, and that was equal to capital W, which is units of watts, divided by m dot, which has units of kilograms per meter cubed. But if you remember right, we divided that entire equation by G. And that ends up being equal to H pump. So H pump is equal to lowercase W dot pump divided by G, or uppercase W dot, which is units of watts, divided by M dot and G. So in this case, we have H pump is going to be equal to 200 watts, which is the wattage of our pump. Now, not all of that energy is going into our fluid, so we have to multiply it by its efficiency, which is 0.8. And then we divide that by m dot, which is our flow rate times our density, right? Because remember, m dot is equal to Q times rho, which is equal to V times A times rho, right? So this is 1,000 kilograms per meter cubed times 1 times 10 to the negative third meters cubed per second times 10 I rounded up here, times 9.8 meters per second squared. Great. So when we solve for that, we get that HP is equal to 16 meters, roughly. So HP is adding 16 meters worth of energy into our flow, which is fantastic. And if we plug that into here, remember all these pressures cancel out, Z out cancels out. We're solving for Zn. We know our velocities, or we know our V out, our Vn cancels out actually. We know our head losses. We've already calculated those up above. We find out that our pump, our new 8 Zn is equal to 8.2 meters, which is still actually, frankly, ridiculous. 24 feet tall tank. You never see those except for in some extreme situations. How else could we reduce the height that we need? Because 8.2 meters is ridiculous, right? Well, the key to that, still, overwhelming all of our head losses are major head loss. So if we go back up to our major head loss term, here's a good example here. FL over D V squared over 2G. So we can't change our length, let's assume. That's stuck, right? We can change our diameter of our pipe. So our diameter of our pipe, we could increase the diameter of our pipe, and that would drive, since it's on the bottom, it would drive our head loss down. It would also have the combined effect of, since we want a certain flow rate, if we increase our diameter, it would also decrease our velocity, but that's term squared, so then we get like double the benefit by increasing our diameter. By the way, that's why if we looked at our flow rate is equal to, remember for our laminar flow with fully developed laminar flow equation, we had pi times delta p times d to the fourth divided by 128 u times L. The reason why d to the fourth is because when you change d, you also change the velocity, which means you get like multiple effects right here, right? And frankly, we could change our friction factor. Remember, our friction factor is a function of our Reynolds number and our L over D. If you look at your Moody chart, we'll draw one here roughly. It goes down like this. So as we decrease our roughness, our E over D goes down and our friction factor goes down. So we could decrease our roughness. And as we decrease our, what's interesting is actually as we increase our Reynolds number, our friction factor also goes down. So increasing our diameter gives us an additional benefit of increasing our Reynolds number. So this goes down. But more importantly, yeah, right. So basically though, the only surefire way to decrease your friction factor is to decrease your roughness on your pipe. So we could also decrease our roughness. Excellent. Then one last question is, what is the minimum pump power needed to get this flow rate at any height? So it doesn't matter what height the tank is, we want to solve for that. And so to do that, we would go back to our equation, which was P over rho G plus V squared over 2G plus Z out equal to P over rho G plus V squared over 2G plus Z in plus H pump plus sum of our H losses. So our flow rate hasn't changed, which means our velocity hasn't changed, which means our head losses are the same as before. Again, we can keep using the same assumptions as before. So our gauge pressure means we can cancel out all of our pressures. Our Z out is equal to 0. Our V in is basically equal to 0. We are now solving for a pump power needed so we don't have to have any height, which means our Z in is going to be 0. Our V out we know, and we're solving for our HP. And so if we plug this in to this equation, we find out that our H pump has to equal 24.2 meters, which we knew, right? We actually solved for that because that was the height needed. So we could have just plugged that into here. And this is with a reentrant, or this is with a curved entrance. If we had used a reentrant entrance, it would be, what, over 30 meters worth of HP. And then we can just plug this back into our equation now. So HP is equal to W dot divided by M dot times G, which is equal to W dot divided by 1 kilogram per second times 9.8 meters per second. And we find out that and that's equal to, like I said, that's equal to 24.2 meters. So we find out that our W dot is equal to 237 watts, which is not much at all. Right? That's less than what a toaster consumes. It's approximately what a high-end laptop consumes. That's not much energy at all. And so it's not hard to get like medium flow rates with adding a pump, right? It doesn't require a lot of energy to do, a lot of power, I should say. Excellent. So now we're going to just record a couple more videos where we just do practicing of this equation.